Today we're going to calculate the distance the Earth travels in one orbit around the Sun. And in order to do this, we're going to use calculus. Well, to get started, I got some data from Wikipedia. And we're going to call A, which equals the semi-major axis. And that equals 92.96 times 10 to the 6 miles. And E, which we're going to call the eccentricity, that equals 0.0167086. And as we all know, the Earth travels in an elliptical orbit around the Sun. And with this data from Wikipedia, our A and E, we can formulate the equation of said ellipse. And that will be x squared over a squared plus y squared over a squared times 1 minus e squared equals 1. And here I tried to make a drawing of the ellipse here. And our semi-major axis is a, so that'll be the limit of the x coordinate minus a to a, and our y coordinate then goes from minus a square root of 1 minus e squared all to plus a square root of 1 minus e squared. So we can kind of pretend the Earth is on this line here and it travels around. And you might say, well, the Sun is in the center. No, the Sun is not in the center. It's at a focus. The focus, there's two foci in an ellipse. One of them would be right here, and the other one would be right over here. The Sun occupies one of the foci. Okay, and from calculus, as we all remember, the arc length of a differentiable function, call it y of x, from x1 to x2 is defined as the integral from x1 to x2 of the square root of 1 plus y prime squared dx. And in our case, we find the arc length of y of x, which is the equation of our ellipse, from 0 to a, and then we simply multiply that figure by 4 using symmetry. So what I'm saying is, let's just figure out the arc length from right here going down to here, just that first quadrant. And then by symmetry, we can tell that there's actually 4 of these, even though my drawing is not very good. Okay, well, we start with our equation, x squared over a squared plus y squared over a squared 1 minus e squared equals 1. That's the equation of our orbital ellipse. And solving for y, which we must do, y equals the square root of 1 minus e squared times the square root of a squared minus x squared. At least that is y in the first quadrant. You might be worried about plus or minus signs here with all these square roots, but in the first quadrant, everything is positive. And if we do our differentiating by our chain rule and so forth, we'll get y prime equals minus the square root of 1 minus e squared times x all over the square root of a squared minus x squared. Okay, so let's plug that into our formula here. And we're going to go from 0 to a, right in that first quadrant. And like I said, we're going to multiply this by 4 to get the entire ellipse. So we have 4 times the integral from 0 to a of the square root of 1 plus, now we're just going to square the y prime, which is 1 minus e squared x squared over a squared minus x squared dx. Now we run into a little bit of problem here because this integrand right here, there is no antiderivative for that. This is known as an elliptic integral, and there's a proof saying that there is no antiderivative for this in terms of elementary functions. So we'd have to go power series and such. But anyway, there are many ways to calculate this numerically. All I did was we plug in our A and our E here, and I just ran it through Mathematica, the n integrate in Mathematica, and the answer I got was approximately 5.840 times 10 to the 8th miles. And comparing that into the recorded figure in the literature, it's exactly the same amount. So, I thought this was very, very good approximation to the orbital distance that the Earth travels around the Sun. And if you like this video, think about giving it a like.